Hello, and thank you for coming. So this presentation is about the paper titled CAPABARA, a combined attack on CAPA. So as the name calls, in this paper, we propose a combined attack on the CAPA countermeasure, which was proposed in Crypto 2018. It's the countermeasure proposed against combined attacks. And our attack, CAPABARA, breaks the countermeasure within its own adversarial model. And in this work, we also propose some fixes, but these fixes do not fully prevent the attack, and they only increase the attack complexity, and for some cases, they create a new vulnerability. So I already talked about some combined attacks, and let's see what they are. So cryptographic algorithms are designed to be secure against cryptographic attacks, but the implementations of them are still vulnerable to physical attacks that are targeting the physical characteristics of the implementations. So we have three types of physical attacks. First, side channel analysis, and this is a passive kind of attack. And side channel analysis exploits the observable leakage arising from the physical characteristics of the implementations. And this is like power consumption of timing of the encryption, or like whatever the cryptographic computation is. And masking is the most commonly used countermeasure against side channel analysis. And in principle, what masking does is it splits the secret information into a number of shares, and in a way, such that the shares are statistically independent from each other. And after that, what happens is, if an adversary observes one of the shares, then they get no information regarding the secret information because they're already statistically independent from each other. Unlike the side channel analysis, fault attacks are active kind of attacks, and they intentionally disturb the computations using physical fault injection mechanisms. And this can be clock voltage glitching, EM waves, or laser. And early fault attacks exploited wrong ciphertext, and we can give differential fault attacks or statistical fault attacks as examples. And redundancy was proposed against this kind of fault attacks as a general countermeasure. And what we do with redundancy is we check if the output of the encryption is correct or not. And if it's not correct, then we suppress it so that the adversary cannot make use of it. After redundancy was proposed, statistical ineffective fault attacks was presented. And this is an attack type that exploits the correct ciphertext, and it specifically injects faults to registers or linear operations. After this attack, redundancy combined with masking was adopted as a countermeasure. So with redundancy, we check if the output is correct or not. And with masking, we randomize the effect of the injected fault. So even if the outcome is correct, the adversary cannot make use of it. But yet, CIFA2 was presented. It again makes use of the correct ciphertext, but this time it targets nonlinear operations. And this time with masking, we can't really protect against this kind of attacks. And the third kind of physical attacks is the combined attacks. And the name is quite clear. We just combine the capabilities of side channel analysis and fault attacks. And it might be really intuitive to think that if we combine the countermeasures for side channel analysis and fault attacks, we can protect against this kind of attacks. But unfortunately, this is not the case, and we need much more intricate countermeasures to protect against this complex kind of attacks. And that being said, the CAPA countermeasure, one of the few countermeasures that were proposed against combined attacks, it's simply inspired from multiparty computation protocol SPITS. And in SPITS, full threshold setting is assumed. And in this setting, all but one party can be corrupted. And following the principles of SPITS, CAPA works on shared data, so it makes use of masking. And it makes use of redundancy by employing MechCheck. So there's a MechCheck associated with each secret variable. So we can track if there's a fault injected to secret variable or not. And CAPA claims provable security against higher order fault attacks, side channel analysis, and combination of them. Now, if there's a fault attack or combined attack or countermeasure, we always make some assumptions regarding the adversary model that is carrying the attack itself. So this is the fault model assumed in CAPA countermeasure. It's called the tile probe and fault model. In this model, we assume that the integrated circuit is split into a number of tiles. And this is really similar to the multi-party computation setting. And in this multi-party computation setting, we have a number of parties, and each party has access to a share, and they come together to compute a function on the secret variable without revealing the secret variable itself. So the tile probe and fault model is very similar to this setting. We have number of tiles, and each tile has their own combinational logic, control logic, and PRNG. And each tile is associated with a share index where the data is split into number of shares. And with probing adversary, if an adversary probes a tile, then they get all the information regarding that tile, and the leakage arising from a tile is independent from the other tiles. And we can also say the same for faulting adversaries. If a faulting adversary injects a fault to a tile, then they can inject fault to any variable within that tile. And as I said, CAPA assumes two kinds of capabilities, probing and faulting. For probing, we have DP probing capability. With this capability, the adversary can observe all intermediate variables within previously specified DP tiles, and they get information regarding those variables from beginning of the encryption till the end of the encryption. And they get the values of variables with a probability of 1. And this is much more stronger than the T-probing model. But this model, tile probe and fault model, aligns better with the real-world scenarios because, for example, if an adversary uses EM probes to probe some variables, then they can observe extra variables in that target area. So this actually suits better real-world scenarios. And for faulting, CAPA assumes two kinds of capabilities. First, DF faulting. For DF faulting, an adversary is capable of injecting chosen value faults to any number of precisely chosen variables within a number of DF tiles. For epsilon faulting capability, an adversary is capable of injecting a random value faults to any variable within any tile. So adversary has access to whole circuit. And that being said, we can differentiate in between two kinds of adversaries. And first type of adversary has DP probing and DF faulting capabilities. Assuming the secret data is split into D shares, DP and DF should be smaller than D, and there should be at least one tile or one share which is unaccessed by those two capabilities. So there should be a tile which is not probed and which is not faulted. For the adversary type 2, it's assumed to have DP probing and epsilon faulting capabilities. Again, we have similar constraint for DP. It should be smaller than D, but now we have no restrictions for epsilon faulting, because as I said, it's random faults and adversary can fault anything in the circuit. And now that brings us to the CAPA design, where the actual computations are happening, like encryption or decryption. Design has two stages. First one is pre-processing stage, and the second one is evaluation stage. In pre-processing stage, CAPA generates some auxiliary data that are going to be used in evaluation stage. And how we use them is we blind the secrets and then we unmask them with the help of those data. And we will be denoting those variables with ABC. The evaluation stage variables, they are just secret variables arising in the encryption or decryption. And we will be denoting them with XYZ. And this is going to be clear in the coming slides. And all the computations are done over F2 to the n. So we are in Galois field. And as I said, there's MechCheck used in CAPA. So how we compute a MechCheck for given data X is we have alpha as the Mech key, and the multiplication of alpha and X is the tag. So we associate this tag to each secret variable. And CAPA makes use of Boolean masking. This means there are a number of shares, and if we take the XOR of them in the Galois field we are working, then we get the secret variable itself. And now the multiplication algorithm. This is the most basic nonlinear operation, so I will just describe this one in the CAPA design. let's assume that the inputs are x and y, and we also have the tags of them, and the output is z, which is the multiplication of x and y, and the second output is the tag of z, and everything is shared. Now, let's assume that d is 2, so we have only 2 tiles and 2 shares. And yeah, I hope this gonna ease the notations a bit, but yeah, we will see. So in principle, the tile 0 has the 0th share of all the variables, and tile 1 has the first share of all the variables. And the variables are x, y, the tag of x, tag of y, and now we see a different kind of variable ABC. And we have a spatial name for that. We call it beaver triple. And what is special with beaver triple is when we have the ABC, C should be equal to A times B. Now the first step of multiplication is blinding. First, the tiles compute x plus A and y plus B, which are also called epsilon and eta, but of course they do it with the respective shares they have. Since the shares are already blinded, now they can send them to each other. And what they compute now is they take the share they computed in the previous step and they add it to the share that they received from the other tile. And this is called partial unmasking step. We call it partial because epsilon and eta are unmasked, but the tags are still shared. The third step is MechCheck. And in this step, we check if the tags of epsilon and eta are consistent with epsilon and eta. And I will describe how it's done in the next slide. But now let's assume that the tags are consistent with the variables and the tiles continue with the computation. The last step of the multiplication is the actual computation step, which we call beaver computation. They compute the output shares of z and the tag of z. And this is also happening local. Now let's see how MechCheck happens. The tiles have epsilon and eta. They were already blinded and unmasked. And they also have the shares of tag of epsilon and tag of eta. And they also have the respective shares of alpha. The first step is they compute alpha times epsilon plus the tag of epsilon with the shares that they have. And then they send these variables they computed to each other. Similar to multiplication, they take the addition of the variable they computed in the previous step and take the variable they received from the other tile. And now they're gonna check if these variables are 0 or not. So in principle, if we multiply epsilon with alpha 0 and add it to alpha 1 times epsilon, we should be getting tag of epsilon. And if we do the same for 0th share of tag of epsilon plus first share of tag of epsilon, we should be getting tag of epsilon again. So here what we do is we add those two variables and we check the outcome if it's 0 or not. If it's not 0, then this means there is something wrong in one of the variables. So there's a fault injected and the tiles abort. If they're both 0, then they assume that everything is as intended and they continue with the computation. And now let's see how they generate the beaver triples ABC. First, the tiles draw randoms A0, B0 and A1, B1. And using a securely passive multiplier, they compute C0 and C1 such that C is A times B. After this computation, they compute the tags of A, B, and C. And if you remember how we compute a MechTag is we multiply the data with the alpha key. So now the inputs are shares of alpha and shares of A, B, and C. And now we have the shares of tags. With the MechCheck, we checked if there's anything wrong with the multiplication or not. But we also need to make sure that the beaver triple we are using in the multiplication is actually correct, which means C should be equal to A times B. So we need to make sure of this. And how we do is we use relation verification of beaver triples. So now the tiles have the shares of A, B, C and the corresponding shares. And now as you see, they are making use of another beaver triple, which we call DEF. In a bit, you will see how they use the second beaver triple. The first thing they do is they draw a random R1, and they compute R1 times A and R1 times the tag with the shares that they have. And the second, they use the kappa multiplication that I explained in the previous slide. And here where they use the second beaver triple, because to blind the inputs of the multiplication, we need a beaver triple, and this is where DEF comes into the stage. The output of the kappa multiplication is C tilde, which is R1 times A times B. In the next step, the tiles compute theta and the tag of theta, the corresponding shares of them. And theta actually means that R1 times C plus tilde C. So if there's nothing wrong, R1 times C should be equal to tilde C. And now they check if these values are 0 or not. If it's not 0, then it means C is not equal to A times B, and the beaver triple ABC is not valid, so they reject it. If the both variables are 0, then they continue the same process with the second random that they drove, R2. And this was how the KAPA countermeasure works. And now let's see how the proposed combined attack works. Again, first things first, the adversarial model of the proposed attack. So we assume an adversary that is capable of injecting a single-shot transient fault to a variable in f to the n. And the fault location is loose, meaning an adversary can inject a fault to a number of bits in the target variable. It could be 1 or up to n. And fault timing is precise. And in a bit, we're going to see that fault needs to be injected at the exact time, like after a specific operation and before specific operation. Any type of fault can be injected, including a random fault. And the target of the fault should be a register. And in addition to the faulting capabilities, the adversary should be capable of probing a chosen variable. And as you see, this model stays within the tile probe and fault model. But moreover, it also works with T-probing and gate register faulting models, because we only inject a single fault and we only probe a single value, which is consistent with T-probing and gate register faulting models. And the first step of the attack is the fault injection step. It happens in the pre-processing step in the beaver triple generation. In the beginning, everything goes as I explained. So they draw the randoms A and B, they compute C. And now the adversary injects a fault to A0. And from now on, the tile 0 has the incorrect value of A0. And this means we now have faulty A. And using the value of faulty A and correct B and correct C, they compute the tags. And now what we have is, we have a tag of A, which is consistent with the faulty A, but this tag is not consistent with the original value of A. And there's nothing wrong with B and C and their tags. And after the beaver triple generation phase, we need to check if it's a valid triple or not. And again, everything goes as I described. They draw a random R1, and they compute R1 times A and R1 times the tag. But now, as you see, we have the wrong value of A and wrong value of the tag. They use the kappa multiplication. And in the kappa multiplication, we have a MechCheck check. But nothing goes wrong, because even though we have the faulty A, we have faulty tag, which is consistent with the faulty A. So this also goes fine. And then the tiles compute theta and the tag of theta. And they check if they are 0 or not. And now, the multiplication of A and B becomes, since we injected a fault to A plus delta times B, which is AB plus delta B. So if you see it from the equation, if B is not 0, then fault A times B cannot be equal to C. So what happens is, the triple is rejected if B is not 0. And if B is 0, then it's going to nullify the effect of the fault, and they're going to do this process for the second time with the second random, and they're going to accept the triple. So if the triple is accepted, we know that B is 0, and this only happens with probability of 1/2 to the n. And now we have the fault injected, and the second of the attack is the probing step. And we know that the triple, the fault A, B, and C, passed the relation verification, and now we can use it in the multiplication. And remember it from the first slides, and we use A and B to blind the secret inputs of the multiplication. And this time we compute eta y plus b using b equals to 0, which means the blinded unmasked variable eta is actually the value of y. So if an adversary probes eta, then they get the value of y itself, which is not supposed to happen. So this was the attack itself, and as I said in this work, we also propose a few fixes against the attack. And the first fix is we can compute the tags of A and B before computing C. So in the proposed attack, remember we inject a fault after C is computed and before the tags are computed. So by computing the tags before C, in principle, we can prevent this attack. But what we can do is we can inject 3 faults and we can still do the same attack. So now we have AB, and before the tags are computed, we inject the fault to A. And now we have the wrong value of A. And now we compute the tags of them, and now we have wrong A and the wrong tag, which are consistent with each other. We inject one more fault to A, so we revert it to the original value. Now we compute C on the correct values of A and B. So we have a valid triple now, ABC. And now we inject one more fault to A so that we can get the same situation as the attack as I described in the previous slides. And the second fix is CAPA can randomly choose in between those two beaver triples, ABC and DEF. So we are not changing anything with the attack, but now we have 1/2 probability that CAPA can choose DEF to be used in multiplication. And in this case, we have half of the initial success probability. But now what we can do is we can inject 2 faults, one fault to ABC and one fault to DEF. Then we can make sure that faulty triple is going to be chosen with the same success probability. And we can also generalize this fix, and we can say that multiple beaver triples can be generated in the beginning, let's say M triples, and 2 of them can be chosen for the relation verification. If we again do the same attack, and now we have 1/m probability of getting ABC to be chosen, but what we can do is we can inject faults to all triples, meaning M faults in total, and we can get the same success probability as the initial probability. And the third fix is we can apply a 0 check on C. So if we check if C is 0 or not, then indirectly we check if A is 0 or not, or if B is 0 or not. And remember that the success condition of attack is B equals to 0. So if we apply this check, and if we recheck the triple when B is 0, then we can prevent this attack fully. But what goes wrong is we use B to blind the input of the multiplication. And if we use a non-uniform set of values to blind the secret value, then we might create a new problem because the secret variables are going to be blinded with non-uniform set of values. So as a summary, the attack we propose consists of a single fault injection in a beaver triple ABC, followed by a single probe. The attack is successful if and only if B equals to 0, which happens with probability of 1/2 to the n. And if B is 0, we know that the faulty triple is going to be chosen to be used. So an unmasked variable will occur in the evaluation stage that can be probed. And the good thing is the fault does not need to be repeatable. In each encryption, we can just inject different random value faults. And we also propose 3 fixes, but they either increase the attack complexity or they create a new vulnerability. And that brings us to the end of the presentation.